Fine. Let us first talk about binary star system, which we have already discussed. Right? We have discussed this thing on several occasions. Suppose, let me draw the Rochelle. Okay. Suppose there is a mass m, small mass, and this is a bigger mass. Fine. Let me now draw the Rochelle. So this is the line drawn between them. So maybe approximately I am drawing. So this is more or less, okay, more or less the Rochelle. Fine, good. Fine. So now, suppose during the course of stellar evolution, which we have discussed, this Rochelle is being filled. This one gets filled. That means the outer envelope during the red giant phase, okay, the outer envelope of the star expands, and as a result there can be mass overflow outside the Rochelle. বুঝতে পারছো? There can from the core the shell, what? The outer envelope is expanding slowly and gradually. Now if there is envelope or mass outside the Rochelle, now this is just a concept, it's actually not a real globe, then that mass will escape the gravitational field of this particular star, and then there will be a possibility, say this Rochelle over here, if the mass gets spilled from this part, then the mass which is escaping, what will happen? It will just enter the gravitational field of this star, right? Now see what happens. Suppose there is some mass which escapes from this point, right, and enters the field of this star. This is donor star, this is acceptor star. Now let me draw the trajectory of the mass. First of all, the whole thing is rotating. There is a rotational frame, right? There is rotation of this whole thing towards their common center of mass. So this mass which we are seeing over here, which has just escaped the gravitational field of the donor star, what does it have? It has mass, of course, kinetic energy, next angular momentum, because of this entire rotation, right? So as a result of this angular momentum, this mass will not fall directly onto the acceptor star. This is first point. There will be no such case. Instead, what will happen is this mass will go on a spiraling motion like this around the star. Now, in the first orbit, now I am just saying, considering a single mass, but in reality, a gas, actually, large number of gas particles, molecules, atoms, they have escaped the field. So there is a continuous flow of particles. Now, what will happen after first revolution? It will come and again hit the spiraling stars. Okay? So there can be motions like this also, this also. What will happen as a result of this? Try to understand. Let us consider the velocity component of a gas molecule at this point. How many? We can, right, consider the velocity component. There are in fact two velocity components. One is along the spiraling motion, around the circular path, outside the star, or this one. And another is a vertical component. Okay? Now, initial period when the mass enters this field, in the initial scenario, let me now rub this. Suppose this is the mass. In the initial case, it can come and hit the same old trajectory. Then again something like this. Then again something like this. This will keep on going like this. What do you think will be the effect? The overall effect is that it will have two components, as I was saying. One is around the center, another is vertical. As a result of continuous striking, we are talking about gas particles. So they will keep on rotating and keep on hitting each other. As a result of this velocity component, the normal component, this will average out. But this will remain. This will average out, this too. Okay, this will average out, the vertical part. But this one will remain. And after some time, this has been also observed through simulations. What you will observe is that if this is the star, then you will see that there is a circular type orbit around which the gas now revolves. So in the initial phase, there was gas particles above or below, but there was more or less what you can say averaging out effect, and so more or less now I can see a structure like this. So this is the first part in accretion disk theory. So formation of accretion disk. Next, let us talk about the physics of this disk. What will happen here? Now for that, let me rub this part. Now, yes?
In smaller star master transfer.
English. In smaller star?
In the smaller star, when the mass is like in a circular way, does it get separated from the bigger star?
Of course, because now it is in the gravitational field of this acceptor star. The donor star, it is far away from there. You can just see that now it was within the Roche lobe of the smaller star. So this means it is within the gravitational field of this smaller star. So it will be rotating around this and not the entire system.
But sir, it was a binary system, so how can it get...
Yeah, it was a binary system, but when I am drawing the Roche lobe, I am trying to demarcate. Have you seen Shin-chan?
Yes.
When Shin-chan plays with his friends, they always do a demarcation line. Come on, this is my place, I will be playing over there. So it is like this. This is my own gravitational space. If anything comes, it will don't belong to my domain. Something like that. Okay. Now, you see, the next part of the story is like this. So this is the star. Now let me consider one particular orbit.
Sir, the mass is spiraling, then why?
Not spiraling, in a circular motion right now. Okay. Next.
First of all, why the spiraling path becomes circular suddenly? It is spiraling, then how it becomes
Now spiraling means there is something. What is the meaning of spiraling? Spiraling means like this. Spiraling means like this. That means there is something going on as a result of which its radius is changing. This is spiraling. I have not said that. What I have told you right now is that there was a star, the gas molecules entered the field, and then there was collision among the field and all that, and now they have now settled in say a particular circular orbit. Whether they will spiral or not, that we have to look into this. This is very important. We all like jalebi. It's spiral in nature, but you have to understand, think of it like that. Say this one, this particular point, the radius over here, and again this particular point in a spiral. What is the difference? Suppose I am talking about the same mass. two mass having the same values, right? Same mass. What is the difference between the two of them in the spiral? Number one, their specific angular momentum is different. Their radii are different. So, their Keplerian orbits are obviously different. Their specific angular momentum is different. So, you can say that in a spiral, something happens due to which, if this particle is keep on going into a spiral, then there is something happening due to which it is losing its angular momentum. This is the first point, spiral motion. Otherwise, it cannot go into a spiral. You see, compare the two values, the specific angular momentum is different. Remember, we have got just mv square by r, right? From there we get the Keplerian orbit, and then if I talk about the specific angular momentum, mvr divided by m. This comes out to be around, if we work it out, gmr. Right? This is the specific angular momentum. So this is the whole thing here. So there is something going on, as a result of which the angular momentum is decreasing. Otherwise, it cannot go into a circular orbit of lower radius. Now you can think of the spiral. Now this is one way of talking about spiral. Another way is you can think of spiral as if there are two concentric rings. One is over here, there is a ring around here, and there is another ring over here. There are two circular orbits, but they have got different specific angular momentum. Now something happens because of which the angular momentum, there is angular momentum loss, and so it slowly drifts in its course of motion and settles down into a lower orbit where angular momentum is lower. Any questions? So, the first thing is circular orbit. How do I get that from gravitational physics? mv square by r and gmm by r square. This is the mass we are talking about, and this is the central mass.
Sir, can we get outgoing spiral orbit?
Just a second. Let me first talk about this. Okay. So from here I am getting the value of the V is what? I am getting from here V square R is equal to G into capital M. Right? And then the angular momentum mv square mvr. You will work it out and then you will get this thing, specific angular momentum. So this is what I am saying. Now your question is, can we have an outgoing spiral system? What does this mean? This means that previously the particle was in a lower circular orbit and later on in a higher circular orbit. Now that is possible only if the particle gains angular momentum. What do you think can happen as a result so that particle can gain angular momentum? Think of a scenario.
The speed of the target increase.
Suppose this is a compact object or maybe a planet, say Jupiter. This has got its ring around. Okay. Now suppose a comet comes and hits one of the rings. What will happen? There will be collision. This whole thing will be disrupted. Okay. But the overall scenario is there will be an input in angular momentum and energy and mass. So maybe we have to do simulations to look into that. Maybe what will happen is, as a result of the collision of comet, the orbit will keep on increasing, probably, and then it will slowly settle down. But you have to remember one thing, that when I am talking about the circular orbits, now try to go into one of those circular orbits. What do you see? in one of the circular orbits. In one of the circular orbits, you will see that there are so many gas particles. What I am saying here is that a single line which you are seeing in this diagram, if you go and zoom into this, you will see that there are many. There is a very large column of gas particles over there, and they are just rotating, right? But they are not static. There will be collisions among themselves, the gas particles. While moving, they will collide among themselves. So there will be friction. This is an example of fluid flow, astrophysical fluid flow. So as a result of these collisions and friction, what will happen is that the angular momentum which it has, this particular circular orbit, will keep on decreasing. Now I am not going into the details of that. There are many theories in that, but you have to understand that there is something going on. If I keep it as it is, suppose there is some particle which enters the trajectory, say for example a comet, then we can have an outgoing spiral. But if nothing happens, it keeps on going in a circular orbit, what will happen? Now, very important point. You have to understand that the gas particles that which I am talking about, are they neutral or are they charged? What do you think? There is no reason to believe that they are neutral, right? Who has guaranteed that only atoms and molecules will be there and not just ions? There is no guarantee. So there will be neutral atoms, there will be neutral atoms, molecules, as well as ions will be there. Now if I am talking about ions and electrons, then this is basically a plasma orbiting, right? So this means there will be magnetic field involved. Okay, now there is a very important theorem, a sort of instability, which says that if a plasma even if there is a low magnetic field involved, if a plasma revolves in a circular orbit, like this example, and there is very small magnetic field, then this accretion disk will be unstable. Unstable in the sense that will be turbulent motion between these fluid particles, plasma. And as a result of this turbulent motion, what will happen? The angular momentum will be dissipated. And the scenario is that this is known as magneto-rotational instability, MRI. And the scenario is that what will happen is the following. So this is the star. So now I am looking like this. Suppose this is one of the orbits and this is yet another orbit. So this orbit has radius r1, this orbit has radius r2, specific angular momentum j2, this has got specific angular momentum j1. Okay. Now what will happen? Because of this turbulent motion, slowly the angular momentum will be dissipated in the outward region. So what I am trying to say is, initially the whole thing, suppose you do a simulation, then you will find if I am putting the gas particles in a circular orbit like this, then after a large period of time, what we will observe is that if there is a weak magnetic field over here, I am talking in the context of magneto-rotational instability, then what will happen? This will become unstable, there will be turbulent motion. Okay, and as a result, what will happen is that slowly the angular momentum will be dissipated outward way. And as a result, dissipated outward, it means slowly the particles of this orbit will lose their angular momentum. Once a particle of this orbit will lose its angular momentum, specific angular momentum J is proportional to R. So this means its radius will decrease, right? And the orbit next to it, the particles will gain angular momentum. So their orbit will increase. So as a result, with time, what you will see is that if this is the initial phase, then in the later phase, you will see like this. So there is spreading of disk due to this turbulent motion or viscosity Understand? So disk will spread slowly and gradually. And this magneto-rotational instability plays a very important role over here. I will talk more about this in later class. But today I am just introducing you. Now there is yet another mechanism also, shear mechanism. We will talk about it later on. So today I am just talking about the accretion disk, how it is formed in a binary star context. And we have talked about this, what Oyon was talking about, a comet entering, then outward spiraling situation. So keep this in mind, very important things. Number one, Keplerian orbit. So I have got a circular orbit, number one. Number two, corresponding to an orbit of radius, I have got a specific angular momentum. Now, because of some phenomena, the angular momentum is slowly dissipated outward. So if this is the star, the angular momentum is slowly dissipated outward. So the outermost layer will keep on spreading out, and as a result of losing the angular momentum, the inner one will go closer to the central object. Okay, so overall there is a spreading of the accretion disk with time. Understand? Next concept, what about the gravitational potential energy? Say the mass which is going over here in the inner radius, it will lose tremendous gravitational energy. Gm r divided by r becomes smaller. So gravitational potential energy loss will be huge, tremendous. And this loss will be in terms of heat energy. And slowly, huge, you will observe heat or basically luminosity. So towards the lower part, there will be very huge heat will be released or luminosity will be very high. This is another point. So three important points. I will work out the details in later class.
Sir, how is this different from the contraction due to pressure that we observed previously?
Now, contraction due to pressure, it is a spherical system right now. Here I am talking about, when I am talking about this accretion disk, particularly the structure, the height is very small. Here, the height, h, this is much less than the radius r. This is number one point. The structure is very much different. This is not a spherical system. This you can think as of like a cylindrical system. I am talking in terms of cylindrical system where the h is very small compared to the radius. Number one. Number two, here there is just, I am talking about viscosity, fluid flow. But in a normal star, I don't talk about like that. There is a random motion here, but there is a particular Keplerian orbit inside a normal star, say white dwarf also, you can think of it. There is no orbit like that. It is just random motion. Their degenerate electrons are responsible in a normal star. Atoms and ions, even molecules are responsible. But there is no such Keplerian motion. And there is no mechanism or MRI like that, because of which there will be loss, there will be turbulence. And as a result, there will be loss in angular momentum. There is no such scenario inside a normal star or even a white dwarf. So in a way, this accretion disk is different from that. Of course, we will work out the equation of state of accretion disk as well in later class. But this is more or less the rough idea. Ask me any questions. This you have seen in class 11 also, circular orbit, all that. Today what I have done is that I have talked about different circular orbits, and I am telling you that the particle can go in the same particle can go into from larger circular orbit to a lower circular orbit by losing angular momentum. And later on, think of it, what will happen? Later on, after going, so basically it will keep on, after many periods there will be a spiral, and then there will be an inner radius, and then finally the particle will fall onto the surface of the object. Remember nova phenomena? This is nova. When the particle will fall on the surface, say white dwarf, the temperature will be very high. When the particle falls on it, there will be huge energy released due to gravitational. R will be, the change in R will be tremendous. So enormous gravitational energy will be released in this phenomena, and also the surface temperature of the white dwarf can be very high. So when it falls on it, the fusion will start on the particular hotspot. There will be fusion, as a result of which energy will be released, a spark-like phenomenon, and that is nova. So this is a sort of phenomenon like that. Now here I am talking in terms of nova, but the same thing we also observe in the center of our galaxy also. There we have got a Milky Way. In the Milky Way galaxy we have got a supermassive black hole, and then around the supermassive black hole there is an accretion disk. Now slowly, whenever it eats the matter, the energy will be released, and that energy will be released in the form of jets, relativistic jets. That's a different phenomenon, because there we are talking about accretion around a black hole. Now accretion around a black hole is extremely energetic compared to accretion around a white dwarf or a neutron star. And I have already talked about the fact that in accretion we can have a large number of energy release. Say the expression E equal to mc square. This means mass can be converted to energy. Nuclear fusion is one of the ways of converting mass to energy, right? This is yet another way where you see the particles, when they go from lower or higher orbit to lower orbit, they are losing energy in this way. So there will be heat accompanied also due to friction and all that, and the energy release in this accretion phenomena, this is even more efficient in converting matter to energy. See, suppose this is the star, acceptor star. Okay, this is the acceptor star. Now when this is first getting its first stream of gas, first circle, they collide. Next, there can be collisions in between. Everywhere there can be collisions. Now because of these collisions, what I told you is that the velocity, there will be two components, one this side, another up. Okay, this part of the velocity will slowly get equilibrated, and only this part will remain. This one will remain, and this will equilibrate. So after a long period of time, what you will see that they have, after a long period of time, you will see that they have now condensed into one particular circular orbit. Okay, now let us look into the same picture. This is from the view from this. So we are seeing like this. This is this view. Now let me think about the different view. Suppose the different view is like this. So the different view is, this is the accretion disk, or I will not say this, I will say it has a torus-like structure right now. Now what will happen with time, the particles over there, because you will see the entire height is much less compared to the radius. So this is more or less a thin disk, although this is somewhat torus in structure. Now with time, because of these collisions and all that, previously when they were forming, the thing was even more wide. But slowly and gradually, because of this components, the two components, this will remain and this will equilibrate. So now they are in this particular state. Fine. What will happen with time is that because of the effect of viscosity and shear mechanism, magneto-rotational instability and all that, what will happen is that they will, this is this particular radius, right? They will start drifting. slowly and gradually, so that after a period of time, this will be now, there will be two components. One is in a larger part and another in a smaller part. So basically spreading of accretion disk. Understand? This part will lose the angular momentum and this part will gain the angular momentum. Or you can say like this, the angular momentum is slowly being transported from inward to outward because of the turbulent motion, viscosity. So there is angular momentum transport in the accretion disk. And the origin is the fluid dynamical turbulence, number one, and in the presence of magnetic field, the magnetorotational instability. Basically stress related to both uncharged particles and charged particles as well. Understand? So this is the accretion phenomena. Important, the transfer of angular momentum from lower orbit to higher orbit. And as the particles in the lower orbit lose angular momentum, where they can go? They have to settle down into an even lower orbit, right? Because they are now slowly losing angular momentum. Okay.